something is seriously wrong with our universe. In its latest discovery, James Webb has just detected a key building block of life at the dawn of the universe, upending what we know about the first galaxies. The discovery, a cloud of carbon in a distant and compact galaxy as it appeared just 350 million years after the Big Bang, marks the earliest detection of an element other than hydrogen in the universe. The results have been accepted for publication in the journal Astronomy and Astrophysics, and a preprint version can be found on ARQBio. As co-author Roberto Maiolino, a professor of experimental astrophysics at the Kavli Institute for Cosmology at the University of Cambridge, said in a statement, "Earlier research suggested that carbon started to form in large quantities relatively late, about 1 billion years after the Big Bang. But we found that carbon formed much earlier. It might even be the oldest metal of all." Astronomers classify elements heavier than hydrogen and helium as metals. That's because, aside from hydrogen and trace amounts of lithium, these elements were forged inside the fiery furnaces of stars and distributed throughout the universe by star explosions called supernovas. This process of heavy element production and seeding was once thought to take many star lifetimes before elements heavy enough to form planets were widely available. But new discovery made by James Webb has challenged this preconception. What James Webb found in the remote galaxy known as GSAZ-12, which was 100,000 times less massive than the Milky Way, were traces of oxygen and neon mixed with a strong signal of carbon. Exactly how carbon could have formed so early in the universe's life is unclear, although it could be due to stars collapsing with less energy than initially thought, according to the researchers. As carbon would have formed in the star's outer shells, this could have enabled it to escape and seed the early universe sooner than expected, instead of being sucked inside the black holes formed from the collapsing stars. That means it's not necessarily true that life must have evolved much later in the universe. Perhaps life emerged much earlier. Perhaps somewhere, under some conditions we might even consider too exotic for life. There are living creatures completely unlike us, better suited to surviving, thriving, and building an interstellar civilization in the cosmos. Perhaps they're not made out of familiar ingredients like proteins, but something else entirely, like a crystalline or metallic set of structures. At that point, it simply becomes a game of hide and seek. Is anybody out there? This ancient question, now known as the Fermi paradox, has haunted us for ages, in particularly as humanity casts an ever wider net across the cosmos, capturing evidence of thousands of worlds. The good news? We know vastly more than any previous generation. Our galaxy is crowded with exoplanets, planets around other stars. A healthy percentage of them are small, rocky worlds of a similar size and likely similar composition to our home planet. The ingredients in the recipe for earthly life, water, elements associated with life, available sources of energy, appear to be almost everywhere we've looked. Now the bad news. We have yet to find another Earth with life, intelligent or not. Observing signs of possible microbial life in exoplanet atmospheres is currently just out of reach. No convincing evidence of advanced technology, artificial signals by radio or other means, or the telltale sign of, say, massive extraterrestrial engineering projects has yet crossed our formidable arrays of telescopes in space or on the ground. And finding non-intelligent life is far more likely. Earth existed for most of its history, 4.25 billion years, without a whisper of technological life, and human civilization is a very late-breaking development. Is there life beyond Earth? So far, the silence is deafening. While the chances of finding life elsewhere remain unknown, the odds can be said to be improving. A well-known list of the data needed to determine the likely abundance of life-bearing worlds, though highly conjectural, is known as the Drake equation. Put forward in 1961 by astronomer Frank Drake, The equation is one of astronomy's most famous attempts to answer the question not just about life, but about the top-shelf stuff. Intelligent life with the ability to communicate with beings outside their planet. Microbes or floating sentient clouds don't make the cut. We want aliens that will talk to us. To be clear, this means there could be life out there in the universe that the Drake equation would discount. But in terms of knowing how likely we are to receive alien signals, it's a great way to organize our questions. It starts from a sky-high view of the necessities for life, and then zooms in, each component of the equation narrowing or broadening the possibilities and getting harder to determine. The equation asks first about the average rate of star formation in the galaxy. This doesn't sound particularly applicable to life, but that's the beauty of the Drake equation. It realizes that to have a species, you have to have a planet, and to have a planet, you must have stars. So, we'll start with making stars. For a long time, this was the only number we had hard evidence for. We can measure star formation rates in many galaxies, ours or any other, by looking at the fraction of young to old stars. We also need to understand something called the initial mass function, which explains how many big, little, and in-between stars emerge out of a stellar nursery. This number ends up being a couple, or 1.53 stars born per year, according to the most recent science. This may not sound like much on the face of it, but keep in mind the billions of years the universe has been churning. It adds up quickly. The second number is the fraction of stars that have planets. This was a mystery for a long time. Astronomers could speculate, but until the past few decades, we really didn't have solid evidence. Thanks to Kepler and WASP and all the other exoplanet surveys, we now have a lot of planets and star systems to judge from. Our best guess for this number is roughly 1. That is, there's roughly 1 planet for every star in the galaxy. Of course, some stars, like our own sun, have many planets, and others none, but we're talking averages here. The next question is, once a star has planets, how many of them are capable of supporting life? This is where we start hitting roadblocks. We only know of 1 planet that does have life. We can argue about whether Mars could have in the past. We can define habitable zones where planets can support liquid water on their surfaces. But what about worlds like Europa, with subsurface oceans? What about tidally locked planets around dwarf stars? The number is highly variable. We think it's somewhere between 3 and 5 right now, but that could be higher or very much lower, depending on how you define habitability. And then we start really plunging into the unknown. What fraction of planets that could support life actually develop living creatures? Again, we know of just 1 so far that has. This number is very much an unknown. Is this 100%? Or do we count Titan and Europa and Mars and Venus and say it's only 20% in our solar system? Past this, what fraction of planets with life host intelligent life? Possible good luck here. 100% of the planets with life we know of have intelligent life. On the other hand, out of the millions of species that have existed in Earth's history, only 1 of them has achieved sentience. So maybe the odds are not so great. Maybe there are a lot of planets with giraffes, but none others with humans. This next bit is part of what separates the Drake equation from general thought experiments about the existence of life in the cosmos. It asks how many intelligent civilizations come up with technology that lets them broadcast evidence of their existence into space, purposefully or not. We've been sending out radio waves for decades, and we're only getting louder. It's of course possible for an intelligent civilization to remain quiet, but we're interested in the ones we can communicate with, which means they have to give some signs. The last factor considers how long these civilizations hang around. One that exists for only 10 years before an asteroid destroys it, or destroys itself by nuclear war, will be harder to find than one that broadcasts for hundreds, thousands, or even millions of years. During the Cold War, many argued that it looked like our civilization, and therefore most others, might not make it past the nuclear age. The window between developing radio technology and nuclear weapons was pretty brief for us. On the other hand, you can argue that once a life form escapes off-world and starts to colonize other planets, it becomes much harder to wipe out as an entire civilization. One asteroid or plague wouldn't do it, so maybe those civilizations quickly become immortal. If you combine all these numbers, you can end up with conservative estimates that give a total number less than 1, as in, we are alone in the universe. More optimistic numbers can yield tens of millions of possibilities. Drake's original estimates were between 20 at the low end and 100,000 at the upper end. So, while we're making progress on some of these figures, we've still got a long way to go. Thus, while Drake's list can be a good conversation starter and a useful way to frame the complex questions around the possibility of other life, these days, scientists don't spend a great deal of time discussing it. Instead, they use a narrower yardstick, the habitable zone. Either way, if you want to have life arise in the universe, a planet might not be absolutely required, but it certainly provides an outstanding environment where life's emergence is greeted by a slew of friendly conditions. That means that a certain amount of chemical enrichment, that is a great enough fraction of elements heavier than hydrogen or helium, needed to have been created prior to the formation of the star and stellar system you're looking at. Back in 2022, the total confirmed exoplanet tally passed 5,000 for the first time, and a remarkable set of facts emerged from analyzing which stars had planets around them at all. Almost all of the planets, 98.2% of them, were found around stars that had at least 25% of the heavy element content found in the Sun. The remaining 1.8% of the planets were found around stars that had between 5% and 25% of the Sun's heavy element content, and that no planets at all were found around stars with fewer than 5% of the heavy elements found in the Sun. If you want to have a rocky world that gives life a habitat for surviving and thriving, we need to have enough heavy elements present, and that places restrictions on where, in the evolved galaxies throughout the modern-day universe, such planets are capable of forming. Planets provide the raw elements from which biochemical reactions become possible for life, but another needed ingredient for life's emergence is a source of energy. While a star might not be the only possibility for providing such a source, as radioactive decay, tidal forces induced by a parent planet or large moon, volcanic activity, and other internal and external sources are all plausible, we know that the Sun provides the energy that powers nearly all forms of life on Earth. However, choosing to have a star power the life on a world, however, places enormous restrictions on the types of life-friendly worlds that can arise. For one, you have to have a good location relative to your star. If you find yourself too close to your parent star, the overwhelming heat, winds, and radiation coming from the star will do things like strip the atmosphere away, or heat the surface up to the point where the only liquids that can exist on the world's surface are lava-based. Similarly, if you find yourself too far from your parent star, you'll be too cold and receive too little energy from the star for life to exist on the surface. That's the idea behind what astronomers and astrobiologists call the habitable zone, which describes where, given an Earth-like atmosphere, liquid water will be possible on the planet's surface. Every star's habitable zone is unique, determined by the star's temperature and luminosity, its overall energy output. The brighter your star is intrinsically, the wider and more distant from the star the habitable zone will be. The cooler and fainter your star is, intrinsically, the narrower and closer to the star its habitable zone will be. In our own solar system, the habitable zone is thought to extend inward from Earth's orbit to just slightly farther out than Venus's distance from the Sun, but outward to right about where Mars is located, and perhaps just a little bit farther. Many scientists believe that if Mars were just a fair bit larger and more massive, it may have been just as suitable for life as Earth is, even over long periods of time. However, this poses a big difficulty for stars that are more massive than the Sun. You see, planets require time to cool down once they initially form in order for life to arise on them. A world covered in volcanic activity, where the only oceans are boiled away into the atmosphere, are not exactly what one would call life-friendly, at least based on our current understanding of life. But for stars, the total stellar lifetime is also dependent on the star's mass, which is intimately linked to its intrinsic brightness. This means that stars with more than about 150% the mass of the Sun may not provide good locations for life to arise and sustain itself at all. There's an old saying that goes, "The flame that burns twice as bright lives just half as long." But for stars, the situation is far, far worse than that. The more massive your star is, the more fuel it has in its core to produce nuclear fusion. And so it's no surprise that more massive stars shine brighter than their less massive counterparts. But what's perhaps surprising is that the more massive your star is, the greater the maximum temperature in its core, the larger the core's volume, where nuclear fusion can occur at temperatures exceeding 4 million K, and the faster it burns through the nuclear fuel located within its core. When you add all the cumulative effects together, what you find is that a star that's twice as massive as another lives just 1/8, about 12%, as long. Furthermore, stars evolve over their lifetime by heating up, meaning that any inhabited planet only has a finite amount of time over which it can support life, before its parent star heats up so severely that its oceans boil away and any biological activity gets sterilized. On planet Earth, we probably have about another 1–2 billion years before that occurs. But on a planet around a significantly more massive star, any life that formed would have been sterilized long before it could have evolved into something complex, differentiated, and intelligent. Planets around more massive stars simply run out of time. But this might make less massive stars even more attractive candidates for life, long-term, than stars like our Sun. This might sound counterintuitive at first, because planets around the longest-lived stars, the low-mass ones that fall into the M class, according to astronomers, also known colloquially as red dwarf stars, face two major problems that aren't present on a planet like Earth, which orbit around Sun-like G-class stars. Stars that are lower in mass than the Sun might live for hundreds of billions or even trillions of years, with the lowest mass stars of all persisting for up to 100 trillion years. These two problems they face are significant, but still might not be deal breakers for life. The first one is tidal locking. The distance from a more massive parent body, like a star, to the less massive orbiting body, like a planet, determines the timescale over which the less massive body becomes tidally locked to the more massive ones. Tidal locking is what happened to the Moon orbiting the Earth, and explains why one side of the Moon, the same side, always faces the Earth. Around M-class stars, all planets within what we call the habitable zone will become locked in only a few million years, tops, meaning that they'll always have one scorching hot side that always faces their star and one freezing cold side that never receives direct light from their parent star. There are plenty of planetary scientists who think that this tidal locking disfavors life, as it creates a severe and permanent temperature gradient across the planet, which only spins on its axis once per orbital revolution. However, tidal forces on the planet will heat the planetary core, which could enable the production of a not necessarily needed protective magnetic field, and lead to more volcanic outgassing, which could prevent the atmosphere from being stripped away, and whereby atmospheric circulation could enable liquid water and possibly life, not just in a narrow ring along the day-night border, but in regions extending well onto both the day and night sides. In other words, this tidal locking, while it might seem unusual to us here on Earth, might not be a blocker to life arising and thriving. However, there's also the second major problem that planets around lower mass stars must contend with. This problem is related to flaring activity, and it is serious. Whereas a star like our Sun is only extremely slightly variable, with its energy output increasing by only a few percent every billion years and changing by no more than 0% over even the extremes of the solar cycle. All of the low-mass stars we've observed remain tremendously active and variable, even billions of years after their birth. Red dwarf stars have star spots similar to sunspots that are enormous and can cover up to half of the star's area. Despite emitting much less light than the sun, they frequently emit energetic, X-ray, and ultraviolet-rich flares, all capable of stripping and orbiting planet's atmosphere away. Many have conjectured that this type of stellar activity renders these planets completely uninhabitable. But there's an important caveat there, for the time being. You see, our sun and all stars were once like that too. Active, flare-rich, and frequently emitting ionizing and atmospheric evaporating radiation and particles. But over long enough timescales, a star like our sun settles down into a more stable phase, allowing a steady dose of radiation that hardly varies in temperature or intensity to strike any orbiting planet, what we know and think of as a set of conditions friendly to life. It turns out that the amount of time it takes a star to settle down depends on the star's mass. K-class stars, the class in between a G-class star like our Sun and an M-class red dwarf star, may require hundreds of millions or even billions of years to settle down into a stable phase. But we've seen the older K-class stars reach this state of steady emission. For red dwarf stars, we fully anticipate that someday. But on timescales longer than the present 13.8 billion year age of the universe, those stars will reach a stable phase as well. Even if they strip an orbiting planet's atmosphere away early on, volcanic activity can replenish it, leading to the possibility that life will arise on such a world well into the far future, many trillions of years from now. However, at some point, a long time from now, stars will cease to form. The rate of star formation across the universe has been dropping ever since its heyday 11 billion years ago, and now sits at right around 3% of its maximum, while continuing to fall. Once a galaxy has lost all of the gas within it, it no longer has material capable of forming the next generation of stars, and so the highest mass, shortest-lived stars all begin dying away with time. After a few billion years have gone by, only the lower mass, redder-colored stars remain, and these galaxies become known as red and dead. Massive galaxies near the centers of large galaxy clusters become red and dead the fastest, while isolated gas-rich galaxies will last the longest, engaging in what's known as quiescent star formation for up to trillions of years to come, or possibly longer. In the locations where star formation only proceeds slowly, at a trickle, rather than in massive bursts, it's possible that those gas-rich galaxies will keep on forming stars for up to quadrillions of years. Even once that stops completely, there will be one final set of objects that merges to light up the cosmos for the last time, brown dwarfs or failed stars that eventually inspiral and merge. When they get there, if their mass is sufficient, they can ignite fusion to form a red dwarf. And if the planetary conditions on any orbiting worlds are just right, life might arise and thrive once that star has settled into the stable phase of its life. All of this means, when we put the pieces of the puzzle together, the following opportunities for life. For the stars that exist today, the lowest mass ones will become habitable only after hundreds of billions or even trillions of years have passed, and may remain habitable for up to Shakt 10 to the power of 14 or 100 trillion years. For the stars that haven't formed yet, it's possible that new star formation will bring with it new chances for life, extending up to Yun 10 to the power of 17 or 100 quadrillion years into the future. And for the stars that will eventually form from the mergers of brown dwarfs, they may continue igniting for up to 10 to the power of 21 or 1 sextillion years into the future, before gravitational interactions remove what we think of as galaxies from the picture entirely. All of this comes along with a great deal of uncertainty and unknowns. After all, Earth, even in 2024, remains the only world we know of where life has ever arisen and continues to thrive. The possibilities for life, at least as we understand it, remain varied and ubiquitous, and should be plausible even far into our universe's cosmic future, even if our cosmic home won't be habitable for much longer. In a universe with so many worlds and so many biochemical possibilities, past, present, and future, it would be foolish to assume that the way things unfolded here represent the only reasonable pathway to success. And in the quest of alien hunt, there are some worlds that we've discovered that, scientists believe, may contain alien life and which we could inhabit. Here is a fresh brief. 1. Kepler 186f. One of the most likely candidates for life as we know it is Kepler 186f. In fact, this is a planet that if we could get there, we might be able to colonize with relative ease. Sadly, the world is 490 light-years away, so even using very liberal and generous estimates, it would take us hundreds of thousands of years to reach. The planet was discovered back in April of 2014, just about a year ago. This falls well into the category of potentially Earth-like planets, as it is within the habitable zone of its star, is terrestrial, and is just 10% larger than Earth. Ultimately, Kepler 186f is just the outermost of the 5 known planets in the Kepler 186 system. Kepler 186 is a red dwarf star, which means that it is considerably smaller and dimmer than our own Sun. The Planetary Habitability Laboratory even created an excellent comparison of a Caribbean sunset as it appears on Earth, and how a similar spot might look if it were on Kepler 186f at dusk. 2. Kepler 283c. Kepler 283c was discovered along with a host of other worlds as part of an enormous data dump from the Kepler Space Telescope. This data contained a staggering 700 newly confirmed exoplanets. Keep in mind, just 20 years ago, we didn't know of any planets in other solar systems, so 700 in one go is quite staggering. However, this world is on the border of being able to support Earth-like life. It is about twice the size of Earth and orbits much closer to its home star, which is over 1700 light-years from Earth. But again, due to the decreased size in the star, it is still well within the bounds of Kepler 283's habitable zone. 3 and 4. Gliese 667c, F and 667c, E. Gliese 667cf and Gliese 667c. E would offer an amazing view. Why? They have 3 suns. Because this is a triple star system, these are 2 of the strangest, potentially habitable worlds that we've ever discovered. Like the other worlds covered, both planets fall inside their star's habitable zone, and at just 22.1 light-years away, it would still take some time to get there, but the travel would be a tiny bit more manageable. 5 and 6. Kepler 62e and Kepler 62f. As their names suggest, these Kepler 62 planets are some other worlds that were discovered by NASA's Kepler Space Telescope. These planets would give us a little more room to work with, as 62e is about 1.6 times more massive than Earth, and 62f is just about 1.4 times as massive. These worlds are quite out there, at least as far as our ability to travel goes. They wander through space about 1,200 light-years from Earth in the constellation Lyra. And if you were born on 62e, you would be quite a bit older than you are now. It completes 1 lap around its parent star, which is a red dwarf, every 122 days. 67f has an orbit of some 267 Earth days. Researchers think that both 62m and 62f are water worlds, warm places mostly or completely covered by liquid water. So they would also be absolutely awesome to visit. Imagine how big the whales may be here. But living there long-term might be a bit difficult. 7. Gliese 581d. Gliese 581d is another one of our galactic neighbors in the grand scheme of things. It is basically just around the corner. This world is just 20 light-years away, the closest planet covered on this list. However, despite its close proximity and its location in its star's habitable zone, the planet might have a thick carbon dioxide atmosphere. This would make it rather inhospitable, as we need to breathe oxygen. However, scientists also believe it could be rocky with liquid water. So, although it might not be too grand for us, scientists think that it could harbor stunning rainforests. But even if it does have oxygen, humans would find it a little difficult to thrive there, as it is some 7 times more massive than Earth and about twice its size. Still, since it is essentially in Earth's backyard, we might want to make a go at it anyways if we ever get the tech to utilize interstellar travel. Last, remember that when you watch this video, somewhere in space, the James Webb Space Telescope is observing the TRAPPIST-1 system and its 7 Earth-sized planets, with 3 in the habitable zone of their star. It will take time to collect enough light and analyze the data, but we truly live in an amazing time, where we can for the first time ever collect light from a small, rocky world in the habitable zone of another star and analyze it for signs of life. In other words, we are on the verge of finding out the answer to the 1,000-year-old question. Are there other alien Earths out there? Look up into the stunning sky. Find your favorite star and allow yourself the freedom to wonder. What if we are not alone in the cosmos? That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.